Okay, we have this system of differential equations that we want to solve. The first step is we need to find the eigenvalues and eigenvectors, and that's going to dictate what the next steps are. And to find the eigenvalues and eigenvectors, we first need to find the eigenvalues. And the eigenvalues are just going to be the zeros of the determinant of this matrix, 3 minus lambda minus 2, 2, minus 2 minus lambda. Now we talked about where this comes from in class, but we're just subtracting lambda off of the diagonal, and we're going to set this equal to 0. So the determinant is going to be the product of the diagonal entries minus the product of the off-diagonal entries. And in this case, that turns out to be lambda minus 3 times lambda plus 2 plus 4. Okay, and so what's going to happen here? We're going to get lambda squared minus lambda plus 6 plus, or sorry, minus 6 plus 4, so that's minus 2. And this is lambda plus 1, lambda minus 2. And so we'll say that lambda 1, and if we set this equal to 0, we get that lambda 1 is equal to minus 1, and we get that lambda 2 is equal to 2. And so we want to find an eigenvector associated with each one of these eigenvalues. Okay, so for the first one, lambda 1 is equal to minus 1. What we're going to do is solve the equation 3 minus minus lambda. So 3 minus minus lambda is 3 plus 1. Minus 2, 2. Minus 2 minus lambda. Lambda is minus 1, so minus 2 minus lambda is minus 2 plus 1 times xy equals 0, 0. Okay, so this is going to give us the eigenvector. The solution to this equation is going to give us the eigenvector associated to the eigenvalue 2. And notice that if we just write this as a system of equations, the top equation is 4x minus 2y is equal to 0. And the bottom equation is 2x minus y is equal to 0. Notice that the top equation is 2 times the bottom equation. And if we've done everything correctly, the top equation will be a multiple of the bottom equation, or equivalently, the bottom equation will be a multiple of the top equation. In any case, this gives us confidence that we've done things correctly, and the bottom equation tells us that y is equal to 2 times x. Okay, so any vector of the form 1, 2, where the bottom entry is 2 times the top entry, is going to be an eigenvector associated to the eigenvalue minus 1, as long as we don't take the 0 vector. So in particular, the vector 1, 2 is an eigenvector associated to the eigenvalue 1. Now for the eigenvalue 2, we're going to do something similar. We're going to do 3 minus lambda, so that's 3 minus 2, 2, and minus 2 minus lambda times xy is equal to 0, 0. Okay, so the top equation is x minus 2y is equal to 0, and the bottom equation is 2x minus 4y equals 0. So here notice that the bottom equation is 2 times the top equation, and the top equation tells us that x is equal to 2y. So any vector where the top entry is 2 times the bottom entry is going to be an eigenvector, except for the 0 vector. So for example, 2, 1 would be an eigenvector, but also something like 4, 2 would be an eigenvector. But 2, 1 is somehow the simplest, so that's the one that we're going to pick as the eigenvector. Okay, and so since we have real eigenvalues and they're distinct, the general form of the solution is going to be x of t is equal to c1 times e to the power of lambda 1, so that's minus 1, times t, which of course we'll just write as minus t, times the corresponding eigenvector, or a corresponding eigenvector 1, 2, plus c2 times e to the power of lambda 2 times t. Lambda 2 is 2, so that's 2t times the corresponding eigenvector, which is 2, 1. And this is the general solution to this differential equation.